Okay, let's have a look at these worksheet problems now. So the first problem on the worksheet basically says that when you try to dissolve methanol, you have a solution that's really weakly conducting or non-conducting to electricity. And when you try to dissolve hydrofluoric acid, or HF, you get some sort of solution that's slightly acidic and that is again weakly conducting, so not a very strongly conducting solution. So when we're talking about conducting, we're talking about the ability for electricity to flow through something. And that relates to whether or not something is an electrolyte. And electrolytes are appropriately named because we're using that electro prefix, and that relates to electricity. Strong electrolytes are things that break up completely in solution. And strong electrolytes are things like ionic compounds, or strong acids, or strong bases. Weak electrolytes break up partially into their ions. So in that case, you'll have some undissociated. Dissociation basically means broken up. Undissociated compound plus some ions floating around in solution, and those weakly carry current. And then you have things called non-electrolytes. So non-electrolytes are molecular compounds. So if it's got just nonmetals in it, it's a molecular compound. And these molecular compounds don't break up at all in solution, and they don't conduct electricity well at all. So if you look at methanol here, methanol is CH3OH. All of these things are nonmetals. So when you end up with CH3OH, you can say that it is a non-electrolyte. For that reason, it's not going to break up into ions, and it's going to result in a solution that's not going to be a good conductor. So that explains that first part of this question. Hydrofluoric acid is a weak acid. So if you looked at a solution that contained hydrofluoric acid, basically what it would show is there'd be some undissociated HFs floating around, there'd be some H pluses floating around, and there'd be some F minuses floating around. These ions allow for it to conduct electricity. Right? It's not exclusively broken up in ions because there's some HF still around, so that means it's not a great conductor of electricity, but still can weakly conduct electricity. These things are called weak electrolytes. Okay, it's an acidic solution because this is an acid, and it gives off these H plus ions. So that explains the answer to question number 1. Question number 2 asks you to identify whether or not something is a weak electrolyte, a non-electrolyte, or a strong electrolyte. Again, strong electrolytes, we get strong electrolytes, are ionic compounds and strong acids and bases. Okay, you can look up what the strong acids and bases are. You should have them in your notes. Weak electrolytes are weak acids and bases. So they're all the acids and bases besides the strong ones. A lot of the time acids start with H and bases bases end with OH. That's not going to be the case every time, as we'll see in a minute. Non-electrolytes are all these molecular compounds. Molecular compounds contain two nonmetals. These ionic compounds that are strong electrolytes contain a metal and a nonmetal. If we look at 2A here, right, it's something that starts off with H. So there's something that gives away that it could be an acid. It's an acid, and it's not one of our strong acids, or at least it's not one of the strong acids we listed in our notes. That means it's a weak acid, so we would call this a weak electrolyte. So there's part A done. Part B, you have something that's got all nonmetals in it. Even though it ends in OH, it's still got all nonmetals, C2H5OH. Right, this means it's a molecular compound, and again, molecular compounds are non-electrolytes. Part C here is a little bit tricky, NH3. And it's easy to think that NH3 would be an acid because it has H in it, or even a molecular compound, which I guess it is, but in fact it's a special type of molecular compound. What happens, NH3 is called ammonia. Ammonia will react with water to form an ammonium ion and OH minus. Bases are broadly defined as things that can accept H ions. So basically what happens in this reaction here is this NH3 picks up an extra H, which means it's a base. So even though it doesn't have an OH in it, ammonia is a weak base. So that would be something you'd have to look up. I know I went over this briefly in lecture, so you should have it in your notes. If not, you can always look it up online. So NH3 is a weak base, which means it's a weak electrolyte. The next two compounds, right, KClO3 and CuNO3 are both ionic compounds. They contain metals and nonmetals. And the first one is called potassium chlorate. Right, it's got a potassium bound to a chlorate ion. The second one would be copper 2 nitrate. It's got a copper 2 ion bound to 2 nitrate ions. Because they're ionic compounds, they are strong electrolytes. Question number 3 is similar to questions 100 and 102 from the textbook. In this case, you're asked to write the molecular, which is the same thing as a chemical, and net ionic equations for the reaction that occurs when solid chromium-3 hydroxide reacts with nitric acid. So the first thing you have to do is figure out the chemical formulas for a chromium-3 hydroxide and nitric acid. Again, when you see that Roman numeral 3, it means 3 plus. So that means chromium here has a charge of plus 3. You need 3 hydroxides to balance out that plus 3 charge. Likewise, nitric acid, right, it doesn't start with hydro, it's not called hydronitric acid, so you know it's not binary. You can use that ic, the fact that it ends with ic, to figure out what the formula is. So nitric acid has nitrate. Nitrate is NO3 minus, you need 1 H to balance that charge. So the formula for nitric acid is HNO3. This is a neutralization reaction, which is a special type of double replacement reaction, which means that cations and anions are going to switch partners here. That means that our chromium 3 plus is going to end up with our nitrate, and our H plus is going to end up with this OH minus. So again, when the H and OH get together, what you end up with is water. The other thing you'll end up with is this chromium 3 nitrate. And you're not told what state chromium 3 nitrate is in. What you need to do is look up your solubility rules to determine whether or not it's going to be solid or if it's going to be aqueous or what the deal is going to be. Key here is that it's got nitrate in it. All nitrates are soluble. That means they can all be dissolved, so they're likely to be found in aqueous form. So that gives you this skeleton equation before you balance it with chromium hydroxide plus nitric acid gives you aqueous chromium nitrate and water. You can balance it by trying to balance the H's, and away you go. From here, it's a matter of breaking up everything that's aqueous into its constituent ions. On the reactant side, the only thing that's aqueous is this nitric acid. So nitric acid will break up into 3 hydrogens and 3 nitrates. Again, this coefficient carries through. And on the right side of the equation, on the product side, the only thing that's aqueous is this chromium nitrate. And I'll give you chromium 3 plus ion and 3 nitrates. We then got to find the spectator ions here, things that are present on both sides of the equation. There is only one spectator ion in this chemical reaction, and that's nitrate. If we eliminate our spectator ions, you're left with the net ionic equation, which has chromium hydroxide reacting with 3 H pluses to form chromium 3 plus and 3 waters. So that's it for the worksheet problems.